Thanks to CuriosityStream for supporting PBS Digital Studios.
We've been failing to detect dark matter for decades. But finally, the latest failure to detect dark matter may have actually proved its existence. One of these is true. Either most of the matter in the universe is invisible and formed by something not explained by modern particle physics, or our understanding of gravity is completely broken. The debate over which is true has raged for decades, but may finally have been resolved in an unlikely way. The proof that dark matter exists and really is an exotic, unknown substance may have come from the discovery of two galaxies that appear to have no dark matter at all. Today, on Spacetime Journal Club, we'll look at the papers that reveal this discovery. The effect of dark matter was first noticed in 1933 when the legendary Swiss astrophysicist Fritz Zwicky noticed that the galaxies in the Coma cluster were moving too quickly to remain gravitationally bound within that cluster. He guessed the presence of Dunkel Materie, a dark matter invisible to the telescope but whose gravitational effect held the cluster together. As with many of Zwicky's predictions, like the existence of neutron stars and gravitational lensing, this wasn't taken seriously until decades later. The hunt for dark matter began in earnest after the early 70s when Vera Rubin discovered that the rotation rates of spiral galaxies were too fast given the mass of their visible stars alone. They should throw themselves to pieces spinning that quickly. That is, unless a gravitational force of unseen origin was holding them together. Since the 1970s, generations of astronomers have searched for the origin of dark matter, gradually ruling out the possibilities. If it were dust or gas, we'd see its obscuring effect on light passing through it. If it were dark, compact bodies like failed stars or stellar corpses or primordial black holes, then we'd see the warping of light of more distant stars in their gravitational fields. In other words, we'd see their gravitational lensing. All known particles of the standard model of particle physics have likewise been ruled out. If dark matter really is a type of matter, then it must be an unknown type. Generations of experiments to find this particle have also failed to locate the exotic dark matter particle so far. This troubled quest has inspired theorists to explore another possibility. What if the discrepancies in the orbits within galaxies and clusters is not due to an unknown source of gravity, but due to a failure of gravitational theory itself? The first such proposal was MONDS, Modified Newtonian Dynamics, proposed by Mordechai Milgram in the early 80s. The idea is that Newton's law of universal gravitation might change between short distances like within the solar system and large distances like entire galaxies and clusters. Such a proposal doesn't just modify Newton's gravity, but also requires modification of Einstein's general relativity. Over the years, various efforts have been made to refine and justify such a modification. And new proposals keep popping up, like the quantized inertia and dark fluid. That last one is something we covered recently. But no consistent theory has appeared. A few points have come out in favour of the dark matter as matter hypothesis versus the modified gravity schemes. There's gravitational lensing, the warping of light from more distant objects due to the gravitational fields of galaxies and clusters. This has given us an independent measure of the mass of those objects, and those masses were the same as measured from the orbits. The cosmic microwave background fluctuations also give us a measurement of the relative amount of dark matter in the early universe compared to atoms. Once again, roughly consistent with what we measure from other methods. Modified gravity theories have had to work hard to keep up with the mounting evidence that dark matter looks like actual physical stuff. But still, we have an impasse. Astronomers and particle physicists can't find the matter that dark matter is made of, while those who would like to overthrow the underlying theory of gravity struggle to make their models fit all of the observational evidence. But there's one feature common to almost all modified gravity models that could falsify all of them. They pin gravity on the baryons. They say that most of the gravity in the universe comes from normal stuff like stars and gas, in particular the protons and neutrons they contain, they're baryons. That gravity then follows different rules at different distances, giving the illusion of there being more baryonic matter than there really is. In this scheme, baryons on galactic size scales should always produce the effect of dark matter. Dark matter and baryons should never be observed separately. The first piece of evidence that baryons and dark matter can actually be separated came with the bullet cluster. This is a pair of clusters that recently collided. Because galaxies are relatively small compared to the space between, the galaxies in these clusters mostly passed right through each other. On the other hand, the gas in these clusters collided and ended up left at the location of the collision while the galaxies moved on. So, where is the dark matter? If modified gravity models are correct, you'd expect it to be wherever most of the baryons are. In this case, that's the gas. There's about twice as much mass in that train wreck of gas in the middle compared to the stars in the galaxy clusters on either side. The true mass distribution of the bullet cluster was mapped using gravitational lensing, this time the warping of light of galaxies behind that cluster. It turns out that most of the mass is A, invisible, it's not stars or gas, but rather dark matter, and B, it's hanging out with the stars and not the gas. The dark matter also appears to have passed straight through the collision site, which is exactly what you'd expect if dark matter is what we think it is, some exotic weakly interacting particle, but not what you'd expect if dark matter were just a modification of gravity produced by the baryons. Then the mass should be exactly where we see it, hanging out with the gas. Some modified gravity proposals have claimed they are still consistent with the observation of the bullet cluster, so apparently we need more evidence. Cue the new discovery, a galaxy that may have no dark matter whatsoever. This weird object is a so-called ultra-diffuse galaxy, or UDG. These can be the size of the Milky Way, but maybe with 1% of the number of stars as the Milky Way. Peter van Dokkum and Shani Danieli of Yale University and their team were studying one of these UDGs in the neighbourhood of the elliptical galaxy NGC 1052. And this UDG is charmingly named NGC 1052/DF2. But today, we're going to call it Fritz. To understand how Fritz formed, the team measured the motions of stars within that galaxy. First, some bright knots of stars, globular clusters, then the diffuse stars of the rest of the galaxy. Remember that Zwicky and Rubin discovered dark matter in the first place by observing that the velocities were too fast in clusters and in galaxies, indicating an unseen source of mass to hold those things together. Well, this team found the velocities were extremely small, at least compared to similar UDGs discovered in the past. From the stellar orbits, they inferred a mass for Fritz of 130 million times that of our Sun, although with an error bar of 80 million solar masses. For comparison, our galaxy has a mass around 10,000 times greater, the vast majority of which is dark matter. This was intriguing. To determine the ratio of stars to dark matter, the team calculated Fritz's stellar mass based on the amount of light received from the galaxy. This is actually pretty straightforward because we have an excellent understanding of how much and what type of light stars of different masses produce. They got a stellar mass of 100 million suns. That's basically the same mass from the stellar orbits. That told the researchers that we don't even need dark matter to account for the mass of this galaxy. At most, Fritz should have about the same mass in dark matter as it does in stars. But even that would be bizarre, because normally in a galaxy like this, the dark matter would outweigh the stars by a factor of 400. The team has since found a second galaxy in the same group that also appears to be missing dark matter, and they have several more candidates for which they still need to measure velocities. It seems it is possible for a galaxy to be missing dark matter, which is an ironically powerful argument in favour of the existence of dark matter. If dark matter isn't a substance, but rather a modification of the laws of gravity, then it shouldn't be possible to separate it from the galaxy. Yet in this case, that seems to be exactly what happened. The authors have some ideas of how this could have happened, but they emphasize that these are just guesses for the moment. Perhaps these UDGs formed from gas and stars ejected in a past collision with the nearby elliptical galaxy. Or perhaps that elliptical galaxy once harbored a quasar. Its central black hole, underwent a feeding frenzy that blasted enough gas out of the galaxy to form a new mini-galaxy, but without the dark matter. Or perhaps those same quasar winds slammed into some gas exterior to the elliptical galaxy, triggering it to collapse into stars, even without the dark matter that would normally be needed to start that process. Obviously, more work is needed to understand these dark matter light galaxies. Van Dokkum and team are on it, and no doubt many other astronomers will be racing to investigate this weird new class of object. Hopefully, if we can understand how a galaxy can form without dark matter, we can learn more about the nature of dark matter itself, which would be nice. I mean, it only makes up 80% of all matter in space-time.
Thank you to CuriosityStream for supporting PBS Digital Studios. CuriosityStream is a subscription streaming service that offers documentaries and non-fiction titles from a variety of filmmakers, including CuriosityStream originals. For example, you can watch The Hunt for Dark Matter, which looks at how CERN and the University of California, Santa Barbara are working to uncover just exactly how dark matter works and what it may actually be. You can learn more at curiositystream.com/spacetime. So you all seem to have completely understood the holographic universe video on first watch, so there's nothing to say here. Well, UFan did request a new video, the explanation of the holographic universe explained. Point taken, any further explanations will get their own entire videos. Today, we're just going to use the response section to address your humorous comments and also to show some of the incredible artwork you came up with depicting Roger Penrose dressed as Gandalf with a lightsaber and a TARDIS. Okay, maybe just one science one from Tonyface, who muses, "The whole information stored on the surface of a volume idea got me thinking, pick a sphere that encompasses whatever you define of as me, so everything about me can be encoded on the outside of that surface. Could you say that everything I could possibly measure about the outside universe is also encoded on the inside of that same sphere? And thus every closed 2D surface in 3D space is essentially a limit of the knowability of one region about the other." Tonyface, consider a career switch. This is indeed a reasonable interpretation of the universe beyond our cosmic horizon, as a hologram living in the light that will never quite reach us, trapped at the expanding horizon. And that sounds like another entire episode. Okay, to the funnies. Mollify shares with us that tuning into that video randomly was like, "Oh bleep, I just walked into the final exam without ever going to class." So you're saying our videos are like a nightmare to you? Well, at least they're free. Kirk420 informs us that while we may feel that we live in a three-spatial dimension universe of up, down, left, right, forward, back, we're actually in a higher dimensional universe of up, up, down, down, left, right, BA, BA, select, start. That's right, you already have all of the power-ups, you just don't know it. Beldegast points out that Roger Penrose is a Time Lord in four-dimensional space, but looks like a Jedi in a three-dimensional surface infinitely far away. Fleem notes that this is a form of Jedi-Time Lord duality. Triality, guys, triality. He's also a wizard. As our Roger Penrose fan art reveals, here we have a brilliant one from Overdex on Twitter. I see a soldier of Minas Tirith in the background there, but wasn't he Gandalf the White, not the Grey, by the time the Fellowship reached the Tower of Watch? Oh yeah, TARDIS, he time traveled. And also from Twitter, we have Stephen Halliday's brilliant drawing in which the lightsaber blade is the matrix mathematics of the more Penrose conditions. Truly an elegant weapon for a more civilized age. And finally, Roger Penrose as Dr. Gandalf the White on Shadowfax by David Shuley. No funnies here, just wow. David, I'm gonna just go ahead and replace Ian McKellen with Roger Penrose in my mental image of Gandalf.